Hi guys, and welcome to this WACE Academy online lesson on the differentiation rules. This lesson will cover syllabus points 3.1.1, 3.1.2, and 3.1.3. We'll be looking at exponential functions, and specifically getting acquainted with a particular exponential function, e to the power of x. This function has some special properties which will be important for working through a whole heap of real-world material later on. First, we'll look at the differentiation of exponential functions in general, and then we'll look at some of the special properties that e to the power of x has. Let's think back to the formal definition of the derivative of a function. Remember that if f of x is a function, its derivative is given by f dash x is equal to the limit as h approaches 0 of f of x plus h minus f of x all on h. Exponential functions are one where the variable, in our case x, is in the exponent. So functions of the form f of x is equal to a of the power of x, where a is just a real number of some kind. Looking at the derivative of a function of this kind using the definition that we just saw, we get f dash x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. If we replace our f of x plus h and f of x with our a to the power of x plus h and a to the x, we can clean this up somewhat, and we get the limit as h approaches 0 of a to the x outside of a to the h minus 1 all on h. Since a to the x is just a constant with respect to h, we can take that out the front, and we're left with a to the x times the limit as h approaches 0 of a to the power of h minus 1 all on h. Now, for the most part, we need to use technology in order to evaluate this limit in the equation. So for instance, if a is 2, we get that the limit as h approaches 0 of 2 to the h minus 1 on h is approximately 0.693147. Similarly, if a equals 3, we get that the limit as h approaches 0 of 3 to the h minus 1 on h is approximately 1.098612. These limits are irrational numbers that get bigger as our choice of a gets bigger. Now, if we notice that in changing a from 2 to 3, we move from the result of the limit being less than 1 to a result that's more than 1. And this kind of suggests that there exists a number for which the resulting limit is 1. In fact, there is a number for which the limit is 1, and it's denoted by E for Leonhard Euler, who discovered it. It's irrational and roughly equal to 2.718281828 and so on. That is, e is the unique real number such that the limit as h approaches 0 of e to the h minus 1 on h is equal to 1. So now we want to think about what the derivative of the function f of x equals e to the x is. Remember the formula that we arrived at earlier, where we showed that if f of x equals a to the power of x, we know that the derivative is a to the x multiplied by the limit as h approaches 0 of a to the h minus 1 on h. So if f of x equals e to the x, we get that the derivative is just e to the x multiplied by that same limit as h approaches 0. But remember, the property of e in the first place was that this limit is equal to 1. So we get that the result is just e to the power of x times 1, which is just e to the power of x. So remarkably, the derivative of e to the x is e to the x. In other words, d dx of e to the x is just e to the x. It is its own derivative. This is a remarkable fact, and this strange number e, along with another strange number, pi, lies at the heart of many of the most surprising and mind-blowing results in mathematics. Hopefully, as a result of this video, you understand the way that we can look at e through the properties outlined, and therefore that you understand that the derivative of e to the power of x is e to the power of x. We'll show you in the next video how this result can be applied to solve real-world questions. See you next time.